The uncertainty principle. The uncertainty principle is one of the most famous aspects of quantum mechanics. Roughly speaking, the uncertainty principle states that one cannot know all things about a particle at the same time. For example, it states that we can know position or momentum accurately, but it is impossible to know both at the same time accurately. Thanks in advance for watching this video. If you like this video, don't forget to like and subscribe to the channel and activate the bell. It is very important for the continuity of this channel. In classical physics, if we know the forces acting on a particle and know what the position and momentum are at a certain instant t, we can calculate the position and momentum of the particle for any later instant t, with the precision we want to. But in the world of very small things, studied by quantum physics, this is not the case. To better understand what this looks like, suppose we want to determine the position and speed of a car traveling at a speed of 30 meters per second using radar that emits electromagnetic radiation. The radiation is reflected by the car and returns to the radar, which, by measuring the round-trip time at successive intervals, can estimate the car's position and speed very accurately. The car's momentum changes when photons collide with it, but due to the car's great mass, the effect is practically negligible. But imagine what can happen if we take objects much smaller and with much less mass than a car. Let's consider an electron with the same speed as the car. Suppose we are going to use the same radar to make the same measurements. By quantum physics, the effect of the photon colliding with the electron is no longer negligible. When doing the radar experiment with the electron, we are changing the measured values. That is, whether we like it or not, we make an inherent error in the act of measuring. In other words, there is the certainty of uncertainty of the measure. To understand the uncertainty principles of physical origin, let us consider the following thought experiment introduced by Heisenberg. Imagine an experiment in which we are trying to measure the position of an electron. Here the wave-particle duality comes in. Since we know its speed v from the de Broglie relationship, we also know its wavelength. To detect a quantum particle, it would be necessary to use something that has a comparable size to that particle, or a comparable wavelength. So we are trying to measure the position of an electron with photons. We might be able to do so by viewing the electron with a powerful light microscope. For us to see the electron and determine its location, at least one photon of light must bounce off the electron and pass through the microscope into our eye. When the photon strikes the electron, it transfers some unknown amount of its momentum to the electron. Quantitatively, we can make an approximate calculation of the magnitude of the uncertainties. If we use light of wavelength lambda, we expect to be able to determine the electron's position within one wavelength of the light being used to view it. So delta x equals lambda. The oncoming photon has momentum Planck's constant divided by lambda. As a result of the collision, the photon transfers part or all of its momentum along the x-axis to the electron. The uncertainty in the electron's momentum after the collision is as great as the momentum of the incoming photon. delta P equals constant Planck's divided by lambda. The final x momentum of the electron will be uncertain in the amount given as follows. We can multiply both sides of the first equation by this uncertainty. Planck's constant represents the minimum in the product of the uncertainties. Because the uncertainty can always be greater than this minimum, we can rewrite the equation. The quantity 1 divided by 2 times pi was introduced by Heisenberg, and it appears so often in quantum mechanics that for convenience it is given the symbol h bar. This is a mathematical statement of the Heisenberg Uncertainty Principle. It tells us that we cannot measure both the position and momentum of an object precisely at the same time. If we wish to determine the location of an electron moving along an x-axis, we have to decrease the uncertainty delta x, so we should use photons of short wavelengths. But photons of short wavelengths have high frequencies and hence high energies. However, a collision with a higher energy photon will have a great impact of the electron, and the more we change the electron's momentum, less certain the momentum. That is, by decreasing delta x, we necessarily increase delta p. Vice versa, if we want to determine the momentum very precisely, less delta p, we use photons of longer wavelength. We increase delta x, and we become less certain of where the electrons will be located. Heisenberg's uncertainty principle states that the more precisely the position of some particle is determined, the less precisely its momentum can be known, and vice versa. If delta x is the uncertainty in position and delta p is the uncertainty in the momentum, then the product of the two uncertainties can never be smaller than h divided by 2 times pi. Another useful form of the uncertainty principle relates energy and time. If we replace the momentum with energy and the position with time, Heisenberg's uncertainty principle for energy and time is given as follows. To solve some examples, you can use the table below of conversions when necessary. Let's see how Heisenberg's uncertainty principle works. Pay attention in the example. To solve this problem, we calculate the momentum and its certainty. Then we apply Heisenberg's position momentum uncertainty principle. The momentum is mass times speed, and the uncertainty in momentum is the percentage times momentum. The uncertainty principle gives us the smallest uncertainty in position using the equals sign. This is about 772 times the diameter of an atom. Let's see another example. The uncertainty in the J-psi mass is the mass width, and this uncertainty in mass is an uncertainty in its rest energy. So we use the famous Einstein's formula to find the uncertainty in mass. We now use Heisenberg's uncertainty principle for energy and time to find the lifetime. This particle only lasts for this short lifetime. A short lifetime like this is difficult to measure directly, and the assignment of very short lifetimes depends on this use of the uncertainty principle. Now that you know the uncertainty principle, maybe it's time to introduce you to the beginnings of elementary particle physics. Read the following text very carefully, and then we will solve the proposed problem. The estimated mass of the virtual exchange particle for the strong force can be made as follows. Let delta t be the time required for the exchange particle to pass from one nucleon to the other, where it is absorbed and disappears. If we assume the exchange particle travels at a relativistic speed, close to the speed of light c, then delta t needs to be at most about delta t equals d divided by c, where d is the distance the exchange particle travels. That is, d is the range of the strong nuclear force, and delta t is the time interval required for the exchange particle to transfer from one nucleon to the other. We now use Heisenberg's uncertainty principle for energy and time, where delta E is equal to the energy of the exchange particle. The energy and mass are related by Einstein's equation. We can rewrite the uncertainty principle by replacing the energy and time and using the equal sign. We solve this equation for mass. We now use the range of the strong and the weak nuclear forces to estimate the masses of the virtual exchange particles. Japanese physicist Hideki Yukawa used a similar idea to predict the mass of the exchange particle of the strong force, and this led to the discovery of the pi meson in 1947. Electroweak theory predicted that three exchange particles were the carriers of the weak force, and they were discovered at CERN in 19 83.